Hello, my name is Ben Graham, and today I will be sharing the results of a numerical analysis I performed on a quantum well with linearly increasing potential, or what we will call the wedge potential. The problem we are studying is one of a particle trapped in a wedge potential well, which can be seen in the bottom right figure, and this problem is a variation of the finite square well problem, which is a well-known and commonly studied problem in quantum mechanics. And so by studying this finite wedge well, we hope to learn about how the form of the states change as we go from the square well to the wedge well, and also how the spectrum of energy states changes with the wedge angle. To approach this problem numerically, we will be using the finite differences method to compute the differential equation. After using the finite difference approximation, we can encode the Hamiltonian of the system into a matrix. This will in turn allow us to find the energy eigenvalues and energy eigenstates by computing the eigenvalues and eigenvectors of this matrix. And once we have our eigenstates, we can explore the results by graphing these eigenvectors. Now let's go into a bit more depth about the equations we will use to approach this problem. We'll model the wedge potential using the first equation, where U0 is the maximum depth of the well, and alpha is a parameter that varies between 0 and 1 and determines the angle of the wedge, and L is the width of the well. From here on, we'll take L as equal to 1 to simplify the math. Next, we know that the Hamiltonian is the sum of the kinetic and potential energies, so we can write the third equation using the form that we know from before of the momentum operator for a single dimension. And here we will take h bar and m to be 1 to again simplify the math. And finally, the last equation on the slide is the finite difference approximation, which we will be using to approximate the derivatives. From the information we had on the last slide, we can develop matrices for both the kinetic energy and potential energy terms of the Hamiltonian. I'm showing these matrices here as heat maps so we can get an idea of what's going on. I have zoomed in substantially on the diagonal of the kinetic energy matrix just so we can see the fine details, but the matrix is the same size as the potential energy matrix, and that is 1001 terms on each axis. So the three diagonals represent the three terms of the finite difference method in the kinetic energy term, and on the potential energy side, we have one single diagonal representing how the potential energy changes. And so now we can solve the resulting Hamiltonian matrix for the eigenvalues and eigenvectors. Here are the results of the computation of the first 6 eigenstates, and in this case we have the potential function defined using alpha is equal to 1, which is the complete wedge shape. And so at first glance, this looks somewhat similar to the eigenstates that we know for the finite square well, but they do obviously have some major differences and are shifted. But let's take a look at how these states vary with different alphas. So we can see here on this slide that we are varying the value of alpha from 0 to 1, and that's changing the potential function from the uniform square well form into the complete wedge. I just want to make a note here that all the well depths are negative 1000, but they've been normalized for these graphs by a factor of 1000 just to make it easier to read. And so as you can see, when alpha is 0, the probability distributions of the eigenstates start off pretty uniform and evenly spread out across the well. But as alpha starts to increase, the distributions shift towards the deepest or the lowest energy part of the well. Another thing we can get from this graph is if we keep an eye on the energy eigenvalues of the states as alpha increases, if you watch it for a couple cycles, you'll notice that the energy spectrum of the states increases with alpha. And just remember that because the potential well is negative, a smaller negative number in the energy eigenstates corresponds to an increasing energy. Now that we've seen how the wave functions change with varying alpha, let's ask ourselves, do these results make sense? Well, if we first look at the psi 0 state, that being the lowest energy state, we'll notice that its probability distribution is really far to the left of the well. And if we go up to the next state, we can see that it goes a little further to the right, and up to psi 2, even further to the right, psi 3, even further than that to the right, and so on. And this makes sense because as the particles have higher energy, they'll be able to get to points further to the right in the well, where the potential energy needs to be higher to get there. Another way that we can ensure that these results make sense is to look at the limit as alpha goes to 0, as the potential function approaches the finite square well, and we should see that the eigenstates approach those of the finite square well, and that's the figure on the bottom right, and we do see that those look like the finite square well eigenstates. Now, there is one problem with the approach taken here that I want to note in this section, and that's that the wave functions are set to 0 at the bounds of the well, and this is due to the computation method taken. However, for a finite well, those should extend slightly beyond due to quantum tunneling. So, to summarize, let's remind ourselves of what we set out to find. We wanted to find the form, or how the form of the state changed when we went from a square well to a wedge well, and also how the spectrum of energy states changed with the wedge angle. And so we were successful in finding that the states became shifted towards the deeper part of the well and became non-uniform, and that the spectrum of energies increased with increasing angle of the potential wedge. One major next step would be to improve the solving function to ensure that the quantum tunneling effects are accurately modeled. And one interesting relationship that I noticed that I would like to study further is the one between the maximum point in the distribution to the shape of the potential well. And so hopefully that's something I can look into in the future. Thanks for watching this video.